Your embedding index may be 8 times larger than necessary. Sentence transformers can truncate Matryoshka vectors. Then recall at 10 shows how much quality you keep. You'll learn how the pieces fit into a workflow that measures size, speed, and match quality before choosing a smaller vector size. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Big embedding vectors are easy to miss. Teams often use the model's full width by default and only notice the cost later. RAM, disk, and search CPU all rise quietly. Matryoshka embedding dimension compression tackles that waste by keeping the parts of the vector that carry the most signal and dropping the rest. The vectors are nested. The leading dimensions act like layers of detail. Chop off the tail, and you often keep the main matches. The payoff is lower storage and faster dot products. The trade-off is losing some fine distinctions on hard queries. We measure that trade-off with recall at 10. How many of the top 10 results from the full index still show up after compression? Here's our plan. Build a full-size baseline index. Make a truncated index, sanity check a query. Measure search latency by dimension, and then sweep dimensions to pick the smallest size that meets a recall at 10 threshold. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we need a clear baseline of full-width embeddings, so every later comparison has a reference for size and rank. This snippet builds the full-size baseline embeddings with sentence transformers. Teams often start here by default. Every document gets the model's native vector width, and that becomes the reference index for later comparisons. The docs list is intentionally small but readable. Like support knowledge-based titles you might retrieve inside a RAG pipeline. Sentence Transformer loads a Matryoshka trained model, and model.encode turns the text into normalized vectors stored in full. The visible output confirms the full index shape, so every later memory, latency, and recall comparison has a clear baseline. Now that we have the baseline, create a truncated index to see what storage we can recover. This example creates the smaller 128-dimensional version of the same index. Storing 768 dimensions everywhere can silently multiply RAM, disk, cache pressure, and network transfer costs. The important call is still model.encode. But now, truncate dim equals 128 asks sentence transformers to return only the leading 128 dimensions from the Matryoshka embedding. Full.nbytes and small.nbytes make the storage trade-off concrete instead of theoretical. Lowering truncate dim usually reduces vector storage and dot product work, but it can also remove signal the retriever needed. The visible output shows the byte reduction you are buying before checking retrieval quality. A quick sanity check is worth doing before running a bigger evaluation. Make sure compressed vectors still return the obvious top hit. This code checks whether compression changes the first document a query would retrieve. Memory savings are useful only if the retriever still sends the right context into the RAG chain. Q-full and Q-small encode the same query at 2 dimensions. Then NumPy matrix multiplication scores each query vector against its matching document index. np.argmax selects the highest scoring document for each setup, giving a quick sanity check before a wider evaluation. This is not enough to approve production by itself, but it catches obvious ranking drift early. The visible output shows whether the compressed index keeps the same top hit for this query. Sanity checks are cheap. Next, isolate the search cost so we can quantify latency improvements. This snippet measures the vector search part after embeddings already exist. In many RAG systems, query encoding and index search are different budget lines. So this timing group isolates the dot products and top 10 selection. Indexes stores one document matrix per dimension, while QByDim stores matching query vectors. The repeated loop makes the tiny example less sensitive to one timer tick. Then lat records milliseconds per search pass. Larger dimensions do more multiply add work per document, while smaller dimensions reduce that part of the search cost. The visible output gives the measured 128-dimensional flat search latency for this run. With timing and a baseline in hand, we can turn this into a decision. Which dimension is small enough, but still good enough? This example turns the compression test into a small production-style decision. The full 768-dimensional ranking becomes gold, which acts as the baseline behavior to preserve. For each smaller dimension, the code computes top 10 hits and measures how much overlap remains with the baseline using recall. The target threshold prevents choosing a dimension just because it is small. It must retain enough of the original ranking first. If multiple dimensions pass, min passing picks the smallest index that meets the bar. The visible output combines chosen dimension, index bytes, measured latency, and recall at 10, so the trade-off is easy to review. Applied to a real project, the same loop maps directly. Swap in your support KB or product catalog, use your real query set, and run the sweep on the live data that matters. The gold ranking is whatever your production retriever currently returns. Measure recall against that baseline and pick the smallest dimension that preserves business-critical answers. 3 points to keep in mind. Matryoshka compression works while taking the leading dimensions from a Matryoshka-trained embedding. Use it when storage, transfer, or search CPU are the limiting factors. And you can accept a modest drop in retrieval detail. One caution: very small DIMs can hide edge case signals, so always measure recall against a production-style baseline before you roll it out. A practical next step is to run this exact sweep on your support knowledge base and vary the target recall at 10 threshold to see the smallest dimension that still preserves business-critical answers. That single parameter will often expose the best memory versus quality sweet spot for your workload. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.